Greetings, my name is Brian Abraham Hernandez Caro, and I'm a student of Material Science at the University of Guadalajara. Today I'm pleased to present this research entitled Development of Low-Modulus Titanium-25 Tantalum Tin Alloys via vacuum sintering for enhanced biomedical performance. Biocompatibility can be defined as the biological acceptability of non-living materials by susceptible tissues when they come into contact with them. Biomaterials, meanwhile, are intended to interact with biological systems to fully or partially replace tissues, organs, or structural components. Titanium and its alloys are widely used in biomedical applications because they have low density and highly desirable properties such as corrosion resistance, biocompatibility, bioadhesion, failure resistance, and processing versatility, among others, which collectively results in superior performance. Tantalum is a good alloying element for titanium, as titanium and tantalum have attracted attention due to their combination of high strength, a relatively low modulus of elasticity, and corrosion resistance comparable to that of pure titanium. Multiple studies identify tin as a beneficial addition to titanium alloys as it exhibits good biocompatibility in tests for ion release, cytotoxicity, and cell adhesion and proliferation, in addition to excellent corrosion resistance in 0.9% sodium chloride solutions. For this project, it was determined that different concentrations of tin will be used, yielding for samples with concentrations of 0, 2, 5, and 8% by volume of tin. The samples were manufactured using the powder metallurgy technique. The powders were then mixed, PVA was added as a binder, and they were compacted using a universal testing machine. The samples were extracted from the device to proceed with their sintering in a furnace. The sintering process was carried out following isothermal ramps. First, the samples were heated at a rate of 10 degrees per minute up to 500 degrees for 45 minutes. Then, the samples were heated to 1300 degrees, where they were maintained for 60 minutes. And finally, the furnace was cooled slowly to extract the samples. The samples were characterized following metallographic preparation, employing silicon carbide sandpaper for roughing, and alumina of 3, 1, and 0.05 micrometers, in addition to a 0.02 micrometers silica solution for polishing until a mirror finish was achieved. The prepared samples were characterized using X-ray diffraction to determine their composition. Scanning electron microscope, images were taken to analyze their microstructure, and a Baker's microhardness test was also performed to determine their hardness. Electrochemical testing in SPF was used to determine corrosion resistance, and finally, nanoindentation testing was used to determine the elastic modulus of samples. The results of X-ray diffraction analysis shows that the titanium alpha and titanium beta phases are present in the titanium 25 tantalum tin alloys. With the addition of tin, the intensity of the main peaks of the alpha phase gradually decreased. This indicates that the addition of tin allowed a higher proportion of the beta phase to be retained during the cooling. Furthermore, no notable tin diffraction peaks were detected in the patterns. This indicates that this element diffused completely, completely into the titanium matrix during the sintering process, or if any intermetallic compounds were formed with titanium, they were not detected due to their low presence of concentrations in the final composition of the materials. The SEM analysis shows the microstructure of each processed material, which are related to the components to make up the alloys. Image A shows two types of microstructures in the titanium 25 tantalum alloys. The bright areas indicate the presence of tantalum, which stabilizes the beta phase. In other areas, a beta plus alpha microstructure is evident, which forms due to the beta to alpha diffusive transformation. The mechanism of this transformation is based on the nucleation of the alpha phase at the grain boundaries of beta phase and its laminar growth inward, dropping the beta phase during the slow cooling process from temperatures above the transformation temperature of 882 degrees. Figures B, C, and D show microstructures similar to those observed for the titanium 25 tantalum alloy. As the tin content increases, the areas with beta plus alpha microstructures decrease, likely because these elements form solid solutions with titanium, further stabilizing the beta phase and hindering the nucleation of the alpha phase during slow cooling. The sample with the greatest stabilization of titanium beta phase is the one containing 5% tin, as shown in the figure C. After the open circuit potential had stabilized for 3600 seconds, the potential dynamic polarization curves of sintered alloys were obtained using SBF, showing a shift in the corrosion potential toward more positive values as tin was added to the materials, and suggesting a possible trend toward improved corrosion resistance, resulting from greater stabilization of the basic layer that these types of materials tend to form. The curves of thin containing alloys, which are shifted further to the left with respect to their current density, indicates that lower current density values can be achieved, which would imply a lower corrosion rate. The table shows the parameters obtained from the analysis of polarization curves. The current density and corrosion potential values were determined using the Tafel extrapolation method, and the corrosion rate was calculated in millimeters per year. These parameters confirm that the materials containing tin exhibit lower current density values and corrosion rates between 2 and 5 times lower than those of the titanium 25 tantalum alloy. The alloy containing 5% tin, which exhibited great stabilization of this phase, showed the best corrosion resistance with a rate of 0.0106 millimeters per year. In the microhardness test, lower values were obtained for the alloys containing tin compared to the tin 25 tantalum alloy. The lowest value was obtained for the alloy with 5% tin because this composition results in greater stabilization of the titanium beta phase, as discussed earlier in the section of X-ray diffraction test. The, the reduced elastic modulus test showed nonlinear behavior with a trend similar to that observed in hardness, where the titanium 25 tantalum base alloy record the highest value of 66 GPa due to the higher presence of titanium alpha phase. The addition of tin acts as a stabilizer for the titanium beta phase, which has lower structural stiffness, reaching its minimum value in the titanium 25 tantalum 5 tin composition, which has an elastic modulus of 53 GPa, since this point corresponds to the maximum retention of this phase. Likewise, the slightly higher value in the titanium 25 tantalum 2 tin with 58 GPa and titanium 25 tantalum 8 tin with 56 GPa result from incomplete stabilization with residual titanium alpha phase and the solid solution hardening effect of tin atoms in the titanium beta lattice. And finally, what can we conclude of this project? Then first, titanium 25 tantalum thin alloys were successfully produced through a sintering process of 1300 degrees for 60 minutes in a vacuum atmosphere. SEM images reveal the microstructures for each composition in the titanium 25 tantalum and titanium 25 tantalum thin alloys. Titanium beta and laminar titanium beta plus alpha microstructures were observed, with the sample containing 5% thin exhibiting more regions of beta phase stabilization. X-ray diffraction test detected the presence of titanium alpha and titanium beta phases as the thin content in the alloy increased. The main peaks of the alpha phase were attenuated as a result of the retention of a higher proportion of the beta phase during cooling. This effect was most pronounced in the sample containing 5% tin. Materials containing tin exhibit lower hardness values than the titanium 25 tantalum alloy, with the lowest value observed in the sample containing 5% tin. Due to the greater amount of titanium beta phase present, the results for the modulus of elasticity followed a similar trend, with the lowest value being achieved for the alloy containing 5% tin. Therefore, adding tin was beneficial in reducing the impact of stress shielding on biomedical implants manufactured from these materials. And finally, potential dynamic polarization test in simulated body fluid indicated that the titanium 25 tantalum 5 thin alloy exhibits better corrosion resistance under the conditions studied, and in general, materials containing tin had a lower corrosion rate than the titanium 25 tantalum alloy. And that's all. Thank you very much for your attention.